Great. So finally, let's talk a little bit about model selection. So this is when you're trying to figure out what variables do you want to include in the model. So you could make decisions about, maybe I just want to put every variable that I have in my data set in as a predictor to account for as much as I possibly can. Or maybe I want to be very selective and only using a few. So you can go about this in a couple different ways. One of them is statistically, and one of them is theoretically. So I'm going to walk you through a couple of the purely statistical ways to do that, and then I'll talk a little bit about the limitations of doing that and why you want to have this based on a theoretical basis as well. So one thing that you can do is that you can do what's referred to as backwards elimination. So this is basically putting in any variables that might be of interest as predictors to start off with. So I'm calling this full model. So this is running a regression and saving it where there is 4 predictors. There's 3 predictors here. And then you use the step function. Object equals is the variable you just created by running that regression. The direction is backward. So this is going to, if we look down here, it's going to go through. It's going to start with all of the variables that you can have as predictors all in there. And then it's going to look and see what is the weakest predictor. And if it's a weak enough predictor that it doesn't seem to matter, it kicks it out. And then it runs another, and it looks and says, okay, what is the weakest predictor? How weak is it? If it's weak enough that it doesn't seem to matter, then it kicks it out. And then it goes through that in an iterative process that is over and over again until it gets down to where each predictor that's still left in the model is strong enough that it's keeping that predictor in. So in this way, you're getting down to only one of the variables mattering enough. You can also do this in a rougher way, that some people sometimes do, where you run a regression and you see what predictors are statistically significant, and you take out the ones that aren't statistically significant, and you go through that, taking out any non-statistically significant ones until you only have the significant ones left. And that would give you very similar results to doing this. But this is essentially using the AIC values, which compares how good the model is with or without those variables in. So forward is going through the exact opposite process, where you start with a null model. And this is having no predictors in the model. So if you just assumed that all the values were the mean, so you create null model, you use the step function, object equals null model, direction equals forward. And scope tells you all of the variables that we could potentially account for. So here you're listing, I want you to go up to potentially using all of these variables. So we'll run this. And if you look here, what it's doing is it's going forward in the model. So it's starting out with nothing in the model. It's telling you, okay, we can use all of this, and we're going to add things in until there's nothing that accounts for enough variance that we would want to add in anymore. So with this, you'll get a model that only includes the ones that account for enough variance at the end that they seem to matter. So for this, you again are going to end up with Dan Grump with only Dan Sleep. So with this, you're getting only the statistically significant predictor out at the end. So you're actually getting the same from forward and backward stepwise regression here. So in some cases, you'll get slightly different results. In some cases, you'll get exactly the same results for these, but that's ways that you can decide what to keep in. So another thing that you can do is that you can compare the model fit for different sets of predictors. So you can see what the model fit is for this one. So in this case, I'm running this regression, and then I'm running another regression with other predictors. And then I can look at the AIC for those two models. And you can compare between these, okay, how much variance is accounted for. Higher AIC means better model fit, more variance accounted for. So the second model, which had more predictors in it, accounted for more variance. So that's not surprising. It's never really going to go down if you add in more predictors. It's only going to go up if you add in more predictors because you're going to be able to account for more variance. So that's not super informative. And so one thing that you can then do is that you can do an ANOVA. So we're going to be doing an F test to compare these models. And this is going to tell us if that difference in the model fit is statistically significant. And what we see is that the p-value is 0.95. So with an alpha of 0.05, that is not statistically significant. So basically the model fit is statistically indistinguishable when you add in the second variable. This is another way of saying that that doesn't seem to matter. So that's a few different things that you can do is you could compare the model fit with that variable in and without to decide if you should keep it in. You can do the backwards and stepwise deletion. You could do what I said is see if they're statistically significant, keep ones in that are, take ones out that aren't. So that's one thing that you can do that's purely statistical. Major limitation of that is that it's specific to your specific results and your specific test. So that is susceptible to random chance. It could be just the case that with your data, randomly some variables work out and some don't. If you collected another data set, you might get completely different variables that are kept in and kept out. So there's potentially a lot of randomness to that that can be going on. So that can definitely be problematic. That's part of why you want to have a theoretical basis for any model that you have. So this should be based on an argument that you have about how you think that the world works, what variables you think influence an outcome. You can read the relevant research to see what variables are correlated with the independent variable and are correlated with the dependent variable. And you might from that decide, okay, I want to also account for this at the same time, because if the results are redundant with something that's already known, that's not very informative. So that's one thing that you can do. You can also look, and maybe there's research saying that the cause of this outcome is this variable, and other research saying that the cause of it is this other variable, and maybe you want to account for both of those things at the same time. So that's ideally how you're going to build the model, rather than just throwing in things or taking out things only based on statistical significance or only based on model fit. So you can do a lot with these model building analyses, but again, you want to be careful with just doing things by random chance. So at this point, you might be thinking, okay, so what if you want to do more beyond this? There's a whole world of doing different things in regression, but for the purpose of this class, we won't have time to talk about those. So let's say that you have a predictor that's continuous, but your outcome is dichotomous. In that case, that violates that assumption that both are continuous variables. You do something called logistic regression, and you interpret the results very similarly for a logistic regression as for a linear regression. Another thing that you might think about is, can't a variable both be an independent variable and independent variable? So for example, X causes Y and Y causes Z, or maybe there's the cyclical relationship going on, or things of that sort. If that is the case, you can do what's referred to as structural equation modeling, which is where you're going to run an analysis where there's a whole bunch of different regressions being run all at the same time, and then you get model fit indices for that. That is something that is its own standalone course. So again, not something we'd be able to get into here. Another thing is you might be thinking, this seems to assume that all of the data are independent for those independent variables and that they're not grouped together in some way. What if I want to look at continuous variables, but I also want to look at how the data is grouped somehow? So you can actually do both. It's doing something that's basically a combination of regression and an ANOVA, and that's referred to as either multi-level modeling or hierarchical linear modeling, depending on the field that you're looking at. And again, that is something that you would probably take your own course in graduate school, but you definitely can do it. And it, again, builds on all of these basic ideas from regression. So another thing you might be thinking of is maybe I have a whole bunch of data, a whole bunch of variables, maybe hundreds of variables, and I want to understand how all hundreds of those variables are related to each other, or how you can use all of that information to just try to figure out variance in your dependent variable or make predictions about the future. So if you're doing something like that, you're getting into machine learning models at that point, and that starts to become its own field. But actually, a lot of machine learning is built off of these basic things building off of regression. So you don't have to just stop with linear regression. You can move forward with that, but you have to learn even more about statistics to get to that point. So with that, I'll wrap up for this week. Thank you for watching the video. If you have any questions, again, feel free to let me know on the discussion boards, over email, over Zoom conversations, anything like that. And I hope this was helpful for you. We're almost at the end of the semester at this point. We just have to talk about factorial ANOVAs next week, and then we'll be wrapped up with everything. So thanks again. See you next week.